So let's get started. So thanks for coming today. Uh, so I'm glad you chose the classroom. I saw some people in the class out on some hammocks in the lawn on the way here. So that's a quite reasonable choice today. If you know of any places where you can give lectures outside on campus, I'd be interested to know. I tried it once on a whiteboard, and just the acoustics weren't good, and my voice was wrecked for a couple of days afterwards. But if the weather's like this, we should try it. Has anyone had a lecture outside on campus? Yeah. Was it gardening? Really fit. Yeah. Okay. Yeah, that'd be a bit harder. I will scout venues, but if any of you find venues too, then we can enjoy a nice day outside as well. So we're going to talk about distance metric learning today. I'm going to partially I'll do some I'll write, and some parts I have some slides. Before we get started, I wanted to look back at the homework just to point out a couple things. One, we had a small typo in how you would read the file, so that's been corrected. So if you refresh it, if you haven't looked at it yet, you'll be fine. When you look at it, it'll be the right version. If you looked at it immediately after I posted it, you may want to refresh your cache. And then I added another bonus method, a bonus question on some exploratory thing in distance metric learning. So mention this. So what I describe up here is a method that is certainly easier than what I will describe today in class. I don't know if it works. So that's why I put it in a bonus method. But if you try it and you think about it and you figure out why it's worked, then write something up. I'd be interested to know. I recently saw this. I'm like, maybe this would work, but I don't understand quite why. Okay, some people complained when I mentioned the homework was too simple, so I added another bonus. Okay. So in this lecture, I want to cover three different techniques. So let me get into it in the form of distance metric learning. Kind of three different perspectives on the problem. Okay, and the idea is that we would like the you think you have data, which is x1, x2 up to xn in RD, and you kind of would like to define a distance between x1 and x2. Okay, for any xi, xj, you want to find a distance between them, but you maybe don't trust the native Euclidean distance, right? So not equal to x1 minus x2. Just the native Euclidean distance might not be the right thing, right? The units on these coordinates, right? Each xi is going to actually be xi1, xi2, up to xid. And if these measure things like height and weight, which you don't, if I change the units, it will change the meaning of the Euclidean distance. If it's like the population, the elevation, and the year founded, again, kind of combine these in Euclidean distance doesn't necessarily make sense. So I'd like to come up with a Euclidean distance of a sort. We know for a lot of algorithms that using a Euclidean distance does make sense. It's a very useful thing to do. And for things like Lloyd's algorithm for k-means clustering, or if I want to do PCA or something like that, then I want to operate in the Euclidean space. So we're basically going to learn. So we like to kind of somehow learn to go from x to, I'll call this maybe x tilde, which is, I'm going to just multiply by some sort of linear matrix, and I'm going to warp it and stretch it. And after I've done this, it's going to be kind of, actually, it's the wrong way. Let's say x tilde is going to get x times a, right? So I'm going to take my original data x and multiply it by linear matrix and stretch it in the right way, which is basically setting one way of interpreting this, setting how I compare the coordinates to each other. And that's going to give me a data set x tilde, and then I can use Euclidean distance on this. Okay, so we're going to talk, I guess, about three approaches in here. And the first one is not going to quite follow this paradigm, but it's kind of close. So the first one is multi-dimensional scaling. All of these have nice, nice acronyms. Most people know them just as their acronyms. This is just, MDS. This will actually go from a distance to a often low dimensional to a distance d to a low dimensional Euclidean distance. Okay, so I get a distance, but it might not be Euclidean. I only have function access to it. And I want to map it to a low dimensional Euclidean distance, maybe even draw a picture. Okay, the second one will be latent discriminant analysis. Okay, LDA. Okay, and this one will basically go from K clusters to a low D, low dimensional Euclidean. Okay, where the input is I'm going to get data and I'm going to be told what the clusters are. Then I want a Euclidean distance that is somehow respecting those clusters. And then the third I will call linear distance metric learning. Okay, linear distance metric learning. And this one is going to get pairs of close or far points. So I'm going to be given a bunch of pairs of points and say these two have data points I think are similar to each other. These other two data points I think are not similar to each other. And I want to, again, map to a low D Euclidean distance. Okay, and they're kind of different forms of inputs. The second two start from a high dimensional Euclidean distance or just another dimensional Euclidean distance and map. So from Euclidean to Euclidean, but it's kind of figuring out how to scale the parameters, where the first one, multi-dimensional scaling, will be a little bit different, is that it takes in a distance, but it's not yet Euclidean. And I want to make it so it is Euclidean. Okay, so let's go through these. So again, multi-dimensional scaling. Okay, so the input here will be I will think of this as a distance matrix. Okay, it's going to be D in Rn by n. So Dij returns the distance between a value I, between the entry I and the entry j. Okay, so I could think of this as there's a function I call, and I call it for object xi and a function and object xj, and it returns a value. And but eventually what you're going to convert that into is just this full matrix. I'm going to call this for all pairs of things. It doesn't need to necessarily be so symmetric on input. Once I map it to a Euclidean distance, the distance I get at the output is going to be symmetric. Okay, but the input doesn't need to be symmetric. Okay, so if I do xj to xi, might be different than from xi to xj. That would be an okay input. It might be harder, the sort of things you can claim about how well this works is harder to say if the input is not like a metric to start with, but you can take any way of doing this as input. You're given on so on your homework is a distance matrix of the distances between airports in the US. Okay. I think this is kind of the mile distance, but you could think instead it's the cost to fly from one airport to the next airport. Or it could be the number of miles or the number of miles the airplane has to travel, which may not be the same as the straight line distance, right? Because if you're ever flying into Salt Lake City, they often make sure they want to do the approach down the valley, not kind of over the mountain and down. So I guess that's more dangerous. Also, the runway is north-south, right? And so that can distort the actual distance the airplane travels. So you're given these distances, and then you want to find a Euclidean distance which represents those. I've seen people do the work where they have a bunch of routers on the internet. They were trying to do some like detective work and figure out kind of where the routers were located, where Google kept its servers. If you make a query into Google or a large sort of search engine, it doesn't send your query to like Mountain View. It sends it to some local machine that answers the query. And these local machines talk to each other, and you can, by being clever, you can ping the distance in between these machines. And then if you learn where a couple are, you can try and figure out where the rest are using distance metric learning, projecting onto a map, or it's a little more complicated. You can do it onto a sphere, but the similar sort of approaches. Okay, so you kind of want to uncover where things are based on the ping distance between some routers. Okay, and then there was no dimensionality or anything here. It might just be a function call. I don't have a notion of the distance, and the output is going to be for a dimension k, so e.g. k equals to 2, then I want to find a kind of a mapping from each xi to a value zi, which is going to be in Rk, where the distance xi xj is going to be roughly the same as the Euclidean distance in this mapping. Okay, so I kind of want this distances to be represented in this low dimensional space. What can again, this is kind of like principal component analysis. I'm not going to have a strong guarantee like I did for the random projections approach. Okay, I'm going to kind of do a best effort here. There's going to be some like stress property, kind of like the cost of the projection that I'm missing. I want to minimize the amount of distance that I'm missing. And we'll see this will reduce to some kind of, we're going to reduce this problem to something like principal component analysis. All right, so who's seen distance multiple dimensional scaling before? Is this familiar with or new? Okay, great. Okay, there are a number of approaches on how to do multidimensional scaling. What we're going to talk about is classic MDS, okay, or classical, I don't know, classic MDS. It's not the only way to solve this, but this is kind of clearly the most popular. When they say MDS, they are often referring to this method, although there could be other ways of doing it. Okay, and so it's going to have a few steps of linear algebra. Remember, I started with the function d, but I'm gonna think of this as the input is going to be this so I'm going to convert this distance matrix, which is again in n by n, to, I'm going to call this d squared, and I'm put this 2 in parentheses. And by this, I mean that for dij of 2, I'm going to square this, the dij, I'm going to square that entry. So I'm going to individually square all of the entries. Okay, if I do a matrix square, remember it's this, okay, there are 3 squares here. There's the square matrix because it's n by n. That means that the rows and the number of rows and columns are the same. If I have the rows and columns are the same, I can actually multiply the matrix by itself. That would be d squared. Without that would be what without the parentheses around the 2. That's not what I'm doing here. I'm squaring the individual elements. Now it's a matrix where the entry for ij is the squared distance between things. Okay. Okay, we'll kind of get some sense of why we want to do that. The next step is the called double centering. And this one is the most mysterious. And I'll try and explain later what this is doing. Okay. And there's a certain matrix called a centering matrix. We'll call this Cn. And it's In minus 1 over n. And this is the all ones matrix. So this is, I'm going to call this 1 to the power n by n. Okay, so this term here, this is a square matrix, and each term is 1 over n. Right, so it's all ones matrix by divided by n. In is the identity matrix. This one is 1, 1, 1. And so I'm subtracting from the identity matrix, the matrix with everything that's 1 over n. What this is doing is if I multiply this by, I multiply the centering matrix by something, it's doing that first step in PCA where you're having it so it's going to, all the columns, the average value is going to be 0. So it's centering it. So the mean of every column is going to be 0. And this is kind of a linear algebraic way of saying, I'm taking the mean of every column and I'm subtracting it off here. And that's what you can, if you think about this and you play with it a little bit, you can see it's actually doing that. But it's common to write this as this matrix. And we're going to use it twice in this step. Okay, so the double centering, I'm going to get some matrix M, which is going to start with D2, my square distance matrix. And I'm going to multiply it on both sides, okay, by the double centering matrix. So I'm basically centering the rows and the columns. Okay. Okay, I'm centering this, basically centers both the rows and the columns, and I want to do negative 1/2 in front. Okay. Again, we'll kind of see why this makes sense. But let me write down the algorithm first. Okay, we're halfway done with the slide. That means we're halfway done with the algorithm. Okay, the third step is we do an eigen decomposition. All right, so we'll get an do a V and an L matrix, where V are the eigenvectors, L are the eigenvalues of the M matrix, right? So I call my eigendecomposition function, I get eigenvectors and eigenvalues. And remember, this means I can write M as V, L, V transpose. which is actually equals to the L to the 1/2 times the L to the 1/2 transpose, right? I can decompose M into these two pieces, right? I told you when we had these square matrices, we're going to assume it's positive definite. This will be positive definite, and it can always be decomposed into two pieces. These were A and A transpose. Okay, so think I have n data points and an A matrix in some d-dimensional space, and I've done A times A transpose. Now I have an n by n matrix. What we talked about with the connection between PCA and eigendecomposition last week, we talked about A transpose A, and we got a D by D matrix. But if you do A transpose, you get an n by n matrix, and you're getting like the left singular vectors instead, right? So these V's are like the left singular vectors of this unknown kind of data matrix here. Okay, and now I want to go down to a lower dimensional space. So I just project onto the top K eigenvectors. Okay, so this is basically, I'm just returning B is going to be VK of LK to the 1/2, right? So this is saying my data is now captured in this term here, right? This term now captures my data in a Euclidean n-dimensional Euclidean space, basically. I've got, these are the left eigenvectors, so every row is kind of corresponds with the data point, and the L to the 1/2 matrix were like these singular values, and those tell me how much to scale each of those data points in that space. And I'm doing the best rank K approximation. So I'm just taking the first K rows and columns here for maybe K equals 2. Yeah.
Why do you see VL to the 1/2 instead of VL? What is that second?
The second part is because I used to have, you can get a square matrix by having A transpose, right? So when I had a data matrix, which was an n by d data matrix, I can get a positive semi-definite matrix, square matrix, by doing A times A transpose, right? And this is how I get something. And these terms, we'll go back and think about kind of what this is doing in a second, but it's kind of doing the inner product in between each term, and the inner product gives me each entry of the M matrix. Okay, and that is how we should think of this, and we'll relate this to the distance and the square distance matrix. Okay, so now that we've written down the algorithm, we can start to unravel it like a little bit here. But let me just note that this B is going to be in n by K, right? So I'm taking the top K vectors, column vectors here, and I'm scaling, and this is a scaling of each of them. Okay, so these are the eigen vectors, and these are the scalings of them. Okay, so I'm projecting them into a space, and then some dimensions have much more spread in them, and that's how much I spread them out. It's captured. This is a diagonal matrix, so it's just one term is scaling one of those coordinates. Okay, and so this is a whole algorithm. It's pretty straightforward. I think you'll implement it on your homework. Yeah, so you square all the entries to get a squared matrix. You do this simple conversion by the double centering into M, do the eigendecomposition, take the top K things, and it gives you some nice outputs. Maybe I'll try and draw a very simple example, but let me first kind of give some intuition of why it works, right? It's kind of mysterious as to why this works. And it's a really old method. It's like 50 years old. Someone came up with this. I never quite understood why it worked, and this is kind of my derivation. I sort of reverse engineered. And so the intuition we'd like to do is we want to use that if I have, so if I do, if I have this A matrix, I do A transpose, then this will be S, where entries, right? And so this maybe is N by D data matrix, where each of these entries, when I multiply this out, the ith jth entry of the S matrix is going to be exactly AI AJ, the inner product in between. Okay, so if you figure out what that matrix multiplication is doing, it's taking the two rows, the ith row and the jth row, and it's taking the inner product that gives me a value, which is Sij. Okay. And I know I can get, if I have the data in this form as S capturing the inner products, then I can do the mapping from S. We had used M before, but M means something different on the previous slide, right? So if I have S, then I can do eigendecomposition like I did PCA and project onto the top K things, right? Now I can do I plus top K to get kind of mapping into RK, right? So this should hopefully is familiar from what we saw last week, Wednesday. Okay, if we have, because of how it relates to the SVD. Okay. Okay, so I'd somehow like to get this inner product. If I can take my distance matrix and convert it into an inner product matrix, then I do this. And this is what steps 3 and 4 was here, right? Steps 3 and 4 is I assumed M maybe was like this inner product matrix. And then I do eigendecomposition and take the top, project under the top K. Okay. So I somehow want to get this inner product matrix, this the similarity matrix. Okay, but what I have instead is something like AI AJ. And again, I don't have the matrix A, I just have a distance, but I have something like the squared distance. This was my input, XI, XJ. XI and XJ can be some sort of object, right? I define the distance between them. And this is the squared distance, right? I did the squaring, so I started here. And so I'm going to take this Euclidean property of the squared distance, and I'm going to write it as AI squared plus AJ norm squared minus 2 AI dot AJ. Okay, so I can decompose the squared Euclidean distance into this form, where I have the squared norm of each term, add those, that's AI and AJ, and then I minus 2 times this inner product. You've probably seen this before in the one-dimensional set, right? But this is the d-dimensional generalization of this, okay? And this conversion has, this term is Sij, right? So I've somehow gotten this term on the right-hand side, this Sij term I wanted in order to do the eigendecomposition, okay? And I started, right? And I started here, right? Where I have the square term, but I have these other terms I have to worry about. I have to get rid of them. There's a minus 2 that will become a minus 1/2, right? So this is kind of, you're starting to see how it fits together. What do I do with these terms here? Okay, these are the terms that are a little bit confusing to deal with. Okay, but let's assume in my RK space, or maybe in the original RD space, I'm going to set A1 equals the first term. I'm going to set one of them to be the origin. Right? So I'll pick one of the terms, and that's going to be the origin. Okay, so then what does the norm of AI mean? Well, then it means that AI squared is going to be equal to AI minus 0 squared, which is just going to be the distance from xi to x1 squared. right? So if I assume that the first term is zero or any of the terms is zero, well, then my squared norm is actually the squared distance from that first term, because that was at the origin. Okay, so I can plug this in, and now I can actually solve for, I can now say that AI AJ is going to be equal to minus 1/2 times dxi xj squared, which I had in the matrix, minus dxi, or this is x1 squared minus xi, again, or this is xj x1 squared. Okay, so now this is pretty close to the this form for m, right? This was mij should have been this form, right? It was m times minus 1/2 times something's this d squared matrix, and this term looks like the d squared matrix. I have these other terms here, but the choice of x1, that this term was equal to 0, it was an arbitrary choice. This was an arbitrary choice. And you can actually construct the S matrix or the M matrix this way instead, by choosing one of these terms to be at 0. And when you get the embedding, it will place that first term at the origin, and this will work. This will give you basically the same embedding, but a little bit shifted. What the double centering does is it averages over both of these all terms as the choice of the one set to 0. So I'm going to average over each of the terms set to 0 in the first term and the second term. I guess maybe I should swap this in here, but and so that's why I need to double center. And when I do that, then I get it so the embedding, the distance matrix, I get all the points, the average of them is going to be 0. It's a little bit nicer embedding. Okay, so that's kind of why roughly why MBS, kind of why it's doing this double centering step, is so that the embedding will roughly look kind of all the points centered around the origin. Okay, so let me write down a very small example. I don't have this preloaded, sorry, but the rest, I have a lot of other stuff loaded on slides. Okay, and this is one, 7, 7, 8. Okay, this is a distance matrix, right? So let me see this term here. This would be the distance between if I start counting at 1, the second term and the third term here. Okay, and so this is where I'm in R 5 by 5. So I have n equals 5 data points. Okay, and so if I square this, then the 1 becomes still 1, but the 7s become 49s instead. Okay, so now if I embed this, the output I get, and I forget the mapping, but it's going to be a picture that looks something like this. Okay, and so I just want to point out a couple of things about the picture. If I look at the average of all the data points, the origin is kind of in the middle here. This is from some plot I read. I don't know why I don't have the plot in front of me. Notice on the distance, on the input, all the entries themselves are zeros. This kind of makes sense. Let's try and figure out the ones which are very close to each other. Which ones are probably these two? They're maybe 4 and 5, right? These are close to each other. I also have that these two are close to each other. So maybe these are 2 and 3. So maybe this is 4 and 5 and 2 and 3, and this would be entry 1 probably, because it has bigger distances to everything else. Okay, and this is a best kind of, in some sense, two-dimensional approximation. I can now visualize these things, right? So if I did this with the airports, you'll draw a picture and put the airport code on them, and you can hopefully kind of see where stuff lies. This will not be, you could rotate this and have all the same distances. So I haven't found like the best rotation of this. If I rotate around the origin, all the distances stay the same. It still stays centered at the origin. Okay. But it gives a pretty good mapping like this. Okay, so this is distance metric learning. Again, the algorithm is pretty simple, a few steps of linear algebra. And you output, you get this nice, if you set k equals to 2, well, then B is an n by 2 matrix, and you just read off the ith row is the ith data point, and you have 2 coordinates for it. So it's simple as that. And you can plot it. Okay. Okay, let me shift into some slides. Usually I like to talk more with on the when I'm writing, then I can control the pace. But I have a talk I gave on distance metric learning a little bit earlier in the semester. So I'm going to kind of go through parts of this talk I have. I also have, so this was for a visualization audience. But I'm going to kind of, so the goal here will be talking about going from d dimensions, say d equals 1,000, down to the best 2 dimensions you can plot. Okay. And so kind of the common approaches people use, again, are PCA, which we talked about earlier. And I mentioned, t-SNE. t-SNE is a method which is nonlinear. And it has some properties that if your data is initially very well clustered, that they will stay clustered. But if they're kind of a little bit clustered and maybe not, then it does not have, it's hard to guarantee anything about it. Okay, so who's heard of t-SNE? Okay, this like Jeff Hinton, who was a Turing Award winner, was involved in the t-SNE work, and it became very popular. I'm not a big fan. Okay. I think if you're learning something nonlinear, you should do contrastive learning probably. I guess t-SNE is kind of a very simple form of contrastive learning. Okay, instead we're going to talk about the supervised approach, and this is one point in the class we'll talk about supervised methods. So we're going to have labels in some way. So I mentioned linear discriminant analysis is going to use K cluster centers, and I'll talk about some newer work we have done where linear distance metric learning. It's different from the work in the textbook because I think this is the right way to do it. And the textbook is what I described in the textbook is an older method that this works better than. Okay, so let me start with my beef with t-SNE. Okay, if you've seen this, they produce these nice plots. This is from what is this? So this data set, so is this CFAR, that of all these numbers, right? The blue ones are the numbers. It is not given the labels. This is of pixels, a small map of digits, hand-drawn digits, and it can it maps them into this space. And it works kind of amazingly well here in that you kind of see the clusters of the numbers in the space. So it's kind of pretty impressive. It can do this. The reason I don't like it is because when you draw it in 2 dimensions, you start to make visual sort of analogies about the data. You want to say things like, well, this line between the 5s, 3s, and 6s in the orange circles, they look to be kind of in order. Well, in the high dimensional space I started from, were they actually in that order? Was there a nice linear ordering between them? You would like to say things like, well, I can build a linear separator between the 7s and the 4s. 7s and 4s are maybe trickier to separate. They look similar. Does that linear separator exist in high dimensional space? You would think it does if it does in this picture. And if I draw a convex hull around a shape, I think these are the, I don't know what numbers, 2s maybe? The 2s, then is there a convex hull on those shapes that separates it from all the other data, except maybe a couple of stray 4s up there? Okay, does this exist in the original dimensional space, in the original distance? And you can't claim that with the nonlinear method. These are all linear properties that are not necessarily true on the original data, but you would assume they would be true by drawing this picture. Okay, so if I do a linear method like the stuff we talked about in the class, you will be able to, things like PCA or LDA or linear distance metric learning, you will be able to make an inference where if you have linear separators in the projection, then they also must exist. Some linear separator must exist in high dimensions. If you have these convex shapes that capture something, then there is another convex hull of points in the high dimensions which separates it from everything else. And if you have linear sequences, then you can fit a linear pattern. It might be projecting onto a linear pattern, but you can fit a linear kind of regressor through kind of a sequence of things. Okay, so the linear methods allow these linear inferences where the nonlinear things don't. And this is often, I think, people probably make inferences like these pictures would assume, but you shouldn't trust them for if you're doing t-SNE or some nonlinear. Okay. Yeah, it's also generalizable to new data. I've learned a mapping from the high dimensions to the low dimensions. There'll be some matrix, right? We talked about where you wanted a tilde, or I guess we said our data. Our data was, we have X, and I wanted to map it to X tilde, which is in low dimensions and nice. And I'll just have a linear function. This describes the mapping, right? So if I have new data, I just apply the same mapping function again. If I have t-SNE, there isn't a way how to do that. I don't have a mapping for new data into the same dimensionality, reduced dimensions. Okay. Okay, that was my first beef with t-SNE. The other beef with it is this is a picture you can find of t-SNE searching on Google image search. Some science paper. Oh no, these are words. These must be some different classes of words. Adverbs, verbs, and stuff. They projected them. They did some analysis saying, look at all this cool structure we found here. And there's some discussion I've had with some domain scientists who've used this multiple times. It goes something like this. So they say, scientists, cool, I did some science, I did t-SNE, I've got this result, here's what it shows me. I say, oh, so how do you know it's good, right? What makes this result good? They say, well, I measured on some of the data I know, right? I knew that these were verbs and these were adverbs, so I assume other stuff nearby them follows that pattern. So I had some data which I could check it on, and the data I checked it on worked out. I'm like, well, if you have these labels, did you use them to train to find the embedding using the labels? So you wanted those to be close to each other. And they'd be like, no, why would I do that? I ran t-SNE, right? And you say, well, why didn't you do that? And they don't understand that you can do supervised versions of dimensionality. Okay, if you have labels that say these points should be close, then use a method that respects that property. Don't do t-SNE and hope that it worked. Okay? Okay, so let me now, hopefully now I've motivated that you should be looking at methods that can use label or some information to do the projection, and hopefully they'll be linear as well. There's a bunch of other nonlinear stuff that is great. And a lot of these learned models from text to embeddings and stuff, text doesn't have an original space it's in, so of course these are nonlinear. But when you can do linear, I would recommend to do a linear. Okay, we'll start with latent discriminant analysis. Some places, I think Wikipedia calls this Fisher discriminant analysis. And this is the one where your input, you're already given the clusters of points. Okay, so you're given a set of endpoints, or maybe a subset of the points, you're assigned one of K labels. Okay, and I'm given one of these K labels, and here I've drawn them in different colors. There's the blue, green, and the red labels. Okay, and so I'm given this label on these points already. And now I want to find, and they're maybe in very high dimension, and I want to project them down to say 2 dimensions so that the clusters themselves are close to each other, and the clusters within the points within a cluster are close, and the points across clusters are far away from each other. Okay. Okay, so I compute a bunch of things. I compute the let's see, the mu j, which is the mean of class j. So this example here would be mu1, right? This is the blue one is the class 1. I compute the mean of these points. I do this for each class. And then I do something where I'm computing the covariance matrix. So I take the distance from a data point to the mean, and I take its outer product with itself. And I add these up or average them. This gives me the sample covariance matrix of this data. Okay. Okay, and so then I want to average this over all the classes. So I average these covariance matrix over all the classes. So basically, if I measure a distance, I want the distance between 2 points to be small, I want that I'd rather this covariance to be small, right? The distances to their mean points to be small. Okay, so this is the first thing I compute. Again, pretty straightforward. Then I need to compute the mean of the overall class, right? This is mean of everything, overall mean. And now I compare the within class mean to the overall mean. Right, so I look at this and I create a covariance between these vectors, right? So I take their outer product and I have a sample covariance matrix for the k different classes here. So it's going to be a rank K matrix here. Okay, and so I want distances in this space. I basically want to be large. So I want the classes, I want them to be separate from each other, but I'm using the overall mean as the proxy. So I want all the classes to be far from the overall mean, the centers of the classes. Okay, and then once I have these two matrices, right, the within class covariance matrix and the between class covariance matrix, I just, I want to find a direction, U, which is maximizing the between class covariance. So think of drawing a direction U here, right? And I want on this direction, if I project onto this direction, I want so that the differences between the means, this is large, and the differences between two data points, these two data points on average are going to be small. Okay, so I want the between to be large, so I want U to maximize this, and between them to be small, so I'm going to divide by this. Okay, so I want to find the direction maximizing this, and then I want to find the next. Once I factor that out, I want to find the direction orthogonal to U, which is maximizing this quantity that's orthogonal to U, and I iteratively do this. This is exactly the eigen decomposition of sigma W inverse times sigma B. Right, these product of sigma 1 inverse, which is like dividing by sigma W, and multiplying by sigma B. I find the top eigenvectors of those, and that gives me a projection into 2D. And so this is the algorithm. Okay, then I find the top two eigenvectors, and I project onto these top two eigenvectors, and that will give me my low-dimensional embedding that is doing its best to separate each class mean from the overall mean and all the points within a class to be close to each other. Okay, and this is the whole algorithm. Okay, so this, again, this would be pretty straightforward to implement. It's a little bit harder than PCA. You have to do a couple more things, but not that much harder. Okay, I'll show an example that I assigned this homework on my grad class last semester this on glove, and this was going to show you where I took 70 words from this glove embedding from 100 dimensions, and nouns, verbs, adjectives, and I said embed them with PCA, with t-SNE, and with LDA, and it might be Hamid's answer I'm showing. Okay. Okay, and so this is the result from PCA. You see these different classes are overlapping with each other. It's just trying to show as much variance as possible, but not to separate the classes. With t-SNE, with these words, it did, I don't know, it's still kind of overlapping. These clusters get a little bit more separated. These are pronouns, prepositions, and the conjunctions, but the verbs and nouns and stuff are all mixed together. Okay, if I run it with LDA, right, I get this, right, where all the classes are fairly well separated from each other. There are 2 points, which I guess must have been very similar embedded, that were in prepositions and conjunctions. And there's some overlap between the pronouns and the conjunctions, but otherwise things are pretty well separated. Okay, so again, this is, if you have labels and you want to get a two-dimensional projection, this is probably what you want to try. If you have a small number of labels in classes. Okay. Look, let's move on to the third category of things, and this will be linear distance metric learning. Okay, and what this is going to be given is slightly different input. Again, I'm starting with data in RD, but I don't trust the Euclidean distance. And instead of giving a small number of labels for every word, I'm giving pairs of words, which every pair of vectors, x1, x1 prime, x2, x2 prime, I'm going to give it a value similar or dissimilar, right? I want them to be close, or I want them to be far away from each other in the embedding. Okay, and so the goal is to find, again, a linear mapping, which could be a stretching of the space, right? Which so that after I've done that, the Euclidean distance between the similar words should be close, and the Euclidean distance between the dissimilar words is going to be far. Okay, and so when I do this, when I'm doing a linear mapping from, right, remember I said x tilde is going to be x times a. What it's doing is I'm actually defining a Mahalanobis distance in the original space. Okay, so think of these, the Mahalanobis distance is kind of, we talked about in the distance lecture in class. It's a generalization of Euclidean distance where I put this matrix in between here. If I put M equals to the identity matrix and D by D identity matrix, this is exactly the Euclidean distance. But what the M is doing, in this case, the M is going to be A transpose A. Okay, and so I'm taking the original, maybe it's A transpose the way I wrote this. Let's see. This is probably, I think I did A, I think it's A inverse. I think if I do it this other way, if I do it if I write it like this, if I left multiply, then I'm going to get that this will be A transpose A. M is A transpose A. So basically, if I look at just, think of this as A transpose A, then if I look at just this X minus Y transpose, I can write this A transpose A x minus y. And if you just look at this part here, this is just projecting a onto x onto using this a transformation. And also this is minus y, right? And the a is also applying to y for the stuff on the right-hand side. For the left-hand side, it's all reversed because I passed it through a transpose, but the same thing is happening. Okay, and then I'm basically squaring the distances and taking the square root. Okay, so when I do a Mahalanobis distance, if I have the 3 points in the space, if I measure Euclidean distance from the red to the blue point here, okay, the blue point is closer to the red point than the red point is to the green point, right? The blue point is closer. I draw these iso balls of a certain radius from the red point. What a Mahalanobis distance does is it stretches the distance metric. And after the transformation, the green point is now closer to the red one than the blue one, right? In this space here, this is shorter than this distance because it gets to the second isoline and it stops to get to the green, where the blue one has to cross over the second isoline, right? Where in Euclidean, the blue one is inside the second isoline, the green is outside the second isoline. Okay, so I'm stretching the space in some way so that I'm changing the distance, but it's a linear stretch of the space. And it changes kind of the Euclidean balls into these elliptical balls. It's a fixed ellipse around any point I switch it to. Okay, so when I'm doing a distance metric learning, I'm learning this transformation. Okay, and if A is low rank, then I'm doing a projection as well. When A is low rank, what that means is that one of the dimensions is squashed down to 0. All the movement along that direction is meaningless. Well, actually, the ellipse becomes very long and infinitely long in that direction. They're kind of like tubes coming out of the plane. Okay, but that's the inverse of that is me squashing stuff down to 0. Okay, yeah.
So the goal, just to clarify, the goal of linear distance metric learning is here is to learn that M matrix that we apply.
Yeah, that's what we want. How do we learn the M matrix so that we can respect these input pairs? I'm now given some supervision here with similar pairs and dissimilar pairs. I want the similar pairs. Let's say the red and the blue, the red and the green one are similar, and the red and the blue one are dissimilar. They're far. So then this Mahalanobis distance makes the green one within some threshold and the blue one not within some threshold. Okay, if I want to do this, the more data I get, I should be able to do better. Right, so this captures kind of, when I say it captures in all affine transformations. And if it counts for feature scaling. If I have a rotation in the space, it still works. It'll still give me the same distance measurement at the end, and it preserves all this linear structure we talked about. Okay. So we want to look for this M. How can we formulate it? Okay, let me just first mention the method that I described in the book, which is a slightly different formulation. You basically want to find an M, which you're minimizing the sum of the squared distances in the, I guess these are the close pairs, where, I want to minimize the close pairs, right? So I want to minimize the squared distance they do. So minimize the close pairs, but I have a restriction that the sum of the far pairs is less than, let's say, 1 is bounded, so that the far pairs, I can't make the far pairs too small. Maybe this is. In fact, we'll do it so it'll be exactly equal to 1. That keeps it exactly equal to 1. It can kind of set this constraint, and the cool insight is that if you do some iterative updates, you maintain the average distance to all the far pairs to be exactly equal to 1. Okay, and it's kind got some nice insights in here, and I like this argument a lot, so I had put it in the book, but it's kind of, it has a d squared step, which we don't want to do, and this other method will work a bit better. Okay, so again, we're given a bunch of observations. We're going to assume they're drawn randomly from the space of all the distances. There are close and far pairs, and okay, we're gonna model this as, so you could, one way of possibly solving this is assume there must exist some matrix M where you can always have the far points above some threshold tau, right? So that's above some threshold tau, and that the close points are less than some threshold tau measured for some optimal matrix M. Right, so I assume there is an optimal matrix M star, and there is a threshold that generates the labels. I can assume there exists a perfect labeling, okay? But I'm not going to assume that. I'm going to assume instead that given this, I'm going to add noise to the distance before I assign this label. So if something is really close to the threshold, I might accidentally label it wrong. The closer the threshold, the more likely I am to mislabel it. The further from the threshold, I'm less likely to do this. Okay, this will allow me to write down kind of an optimization problem, and I might not have to, and I might get really noisy data where there isn't a perfect solution, and I can still solve kind of the best possible. Okay, okay, and so. What kind of noise? Well, if you think of something like a normal noise, then basically the probability it's mislabeled depends on how much noise I added, and if that was greater, it's mislabeled if the noise I added is greater than the distance from the threshold, right, under some threshold tau and some value n. And I can swap this around. This is equivalent, and that gives me kind of this the integral on the back part of this noise model, like a noise model. It's a little bit easier to work with and equivalent to look at the integral on the front part of the noise model, because this is the cumulative density function of the noise model up to some point. It's symmetric if the noise model is symmetric to x and y, and then I can write this down as kind of some noise function. So if I have a noise model, whether it's normal or like a logit function, which don't worry too much about, then I can write this down as the integral of this function up to some value. Okay, what this allows us to do is to write down an optimization function. There's some empirical risks, so I have n samples of pairs of points, and I want labeling to be described exactly as the probability I get the labels right given the model, but I'm going to take the log of that, the negative log of that, and so the product of a bunch of things all being true, the log of that product, I can push the log through, and some exponential term, I get the log of the noise, which is often easier to work. And so this function will often is going to be convex, is what we'll show. Okay, and then there's a true risk function if I sampled of all possible things, but we can optimize on the sample risk function. And so what we're able to show is that these two risk functions are both convex, which means we can use gradient descent to optimize them over the parameters of the matrix M. Okay, that it's uniquely minimized at the right answer if we have the full data, and that with enough samples, 1 over epsilon squared, which is a term that showed up in a lot of other places in class, roughly 1 over epsilon squared times the size of the matrix M, d squared, from more or less, then we can get epsilon air for any cost function. They're always epsilon close to each other. So if we have enough samples, then we can approximate the true thing. And if we optimize the minimum of the sample function, we can guarantee that we're close to what the true function would be. Okay, so what we've what you can argue here is that if you draw enough samples of pairs of points and you write down the cost function with the right noise model and you optimize that, you're going to approximate the optimal true function from some unknown sort of unknown distribution. Okay. You can also show you can recover the parameters. You get close in the right parameters of the distance, and that you can truncate the distance using like a low rank approximation, and this will give you a low rank metric that you've learned as well. That if the eigenvalues of M are small enough, then you can prove some approximation guarantee in the distance as well. Okay, and this works pretty well. Okay, let me go back and say, basically, this is the algorithm. So I don't really describe the algorithm here because it's gradient descent. Okay, so we're going to write down this cost function here. And you're going to run gradient descent on the parameters M and some threshold tau. Okay, so you can write down these of the this function, and it's parameterized by M and tau, and then you can use AutoGrad if you want to, but the derivatives are not too bad to write down for certain noise functions. Like if you use the logit noise function, it becomes a form of logistic regression. And then you can run gradient descent, and that's the whole algorithm. Okay, so it's not, we haven't used gradient descent elsewhere in this class, but I hope it's not something you're unfamiliar with. Okay. Okay, we're kind of going through this quickly, but let me just say, so you can try different noise models. They're like a normal or logistic noise. And they give fairly similar results. We generate a bunch of data. And so they're far, if and only if this plus some noise that we've added from one of these noise models. And then we try and recover it here. Okay, and I want to zero in on this one picture to say what's going on here. The epoch is the amount of training that we've done, and so it's converging towards some sort of accuracy. The accuracy is what fraction of some data points that we generated in a test set we did not train on, how well those are doing. That's the blue and the green ones are from a test set, and the black and the red ones are from the training set. Okay, so the blue and the red, test and train without noise, they're basically matching each other. And the test and the train, the green and the black are basically matching each other, meaning we're not overfitting. We're not fitting to the wrong answer here. And then the ones without noise, the blue and the red ones are doing much better. What's happening here is these are the labels they would have been given if we did not add the noise before assign the label. So that's the true distance between them without a noisy measurement on that. And the green one is when we are using the labels that have the noise added, and we added enough noise so 10% of them were given the wrong label. And so the accuracy we're getting is basically we're getting to 90% accuracy on the ones that had 10% given the wrong label. We're getting to like 99% accuracy for the ones that were given the right label. So we're basically recovering the right model that it was generated from. Okay, so this, if you assume this noise model works pretty well, what we showed here is if you train with one noise model, but you gave it a different noise model, it does about the same, not quite as well. Okay, so if this noise model makes sense, then we're able to kind of recover stuff almost exactly, even if you use kind of a slightly different kind of symmetric Gaussian-like noise model. Okay, so you can actually add noise. So So if you add noise to what fraction of the data has been misclassified. Okay, so if you look at the green and the pink are the noisy versions. So if I add 30% noise, my accuracy is 70%. Right? So I got 70% right. That's because I mislabeled 30%. But if I add 30% noise and I try and recover the true parameters, I'm still getting like 99% on what the label would have been before I added this. Okay, so this works really well up to like 30% of the data is even mislabeled, as long as you're picking roughly the right noise model. Yeah, so let me say the next thing. How many samples do you need? How many pairs do you need to sample to get high accuracy here? And so this is basically saying that with 45% noise, with 45% of the noise, so the noisy version is not doing very well, but the non-noisy version where I'm recovering the right models, I'm getting above 90% accuracy still. And I get it after about 25,000 samples. Before 25,000 samples, I might maybe 10,000 samples, it's doing okay. But if I only have 100 samples, I'm not going to be doing so well with 45% noise. If you have less noise, then these curves, you can get them higher accuracy with fewer samples. But you have to, but not actually that much more. Right, so you need a fair number of samples for these things to work. This is in 10 dimensions, I think. Okay, and so this is comparing to this EIG-DML thing, which is in the book, where again, this is the number of samples. Yeah, this is 10% noise, so only 1,000 samples. Yeah, okay, so with only 2,000 samples, our model can basically get to 97% accuracy, where the EIG-DML is only getting to like 90% accuracy, right? So this is why I think this method is better than that. It works a little bit better than the one in the book. It's not that much more complicated. That one also reduces to some iterative method. Probably is even a little trickier to implement than the gradient descent one. Yeah, and if you, let's see, if you unbalance what fraction of close and far points do you have? If you have 50-50 far points, 50-50 close points, then it's doing well. But if you get only 10% of one type of points, it starts to drop off. So you want to have roughly balanced data set, but it can be pretty safe between, 90-10 split would be okay. And then what else? Okay, and then I want to say one more trick that isn't on the slides is that one thing you want to make sure to do is you want to normalize your data first. Yeah, this is something I didn't talk about. So let me. So instead of DML, can we just normalize the coordinates, right? And there are two types of normalization. You can look at, say, you have height and weight. So data point xi has xi1 and xi2, which is the height and the weight of a person. And one way I might do it is I could look at all of the x11, x21, x31, up to xn1. These are all the values of height. Okay, and then I can say I want to either set so that the mean of these xij, or that's over over the values I is equal to 0, and the standard deviation is equal to 1. So it'd be kind of 0, 1 normalizing or standardizing. And I could also set so that the min of x over the values I of xij equals to 0, and the max over I of xij is equal to 1. And this would be like 0, 1. I guess this would be min-max normalizing, and this would be kind of standardizing. These are kind of two approaches you can do to kind of put everything on the same scale before you measure a distance between. Okay, so this sometimes works okay. Okay, I can normalize the height and the weight so they approximately are in the same scale. Then I don't have one meaning much more than the other usually. These approaches don't always work, and they're not always the right thing to do. There are some pitfalls to doing these. So I'll say some pros and some cons. So some pitfalls, okay? If you have outliers or new data, then it's going to change the mapping. Okay, so I mean, it could be that I have outliers. I could define the mapping, which is just a linear scaling and shifting maybe. I could do that before I see the new data. But if I have a single outlier and I have a 0, 1 mapping between 0 and 1, and I have one outlier out here and a bunch of data out here, then most of the distances are in that small range, and that outlier has stretched this range. So the 0, 1 mapping is susceptible to outliers. The mean, the standardization with the mean variance scaling also is susceptible to outliers, not quite as extreme as this. And if I get new data, I may want to change what the mapping is. Okay, so it's not, so it can change kind of based on these things. The standardization also kind of assumes it's unimodal, but if the data is bimodal instead, then having a single mean standard deviation doesn't necessarily make sense. Okay, so and the standardization kind of assumes unimodal. Okay, kind of implicitly assumes that. It's not necessary. You can still run the algorithm, but the model doesn't make sense as much to have a mean and variance if it has these multiple clumps to it. Okay, the third pitfall is that if kind of coordinates are collinear, if some coordinates, okay, then if I move along one, I also get the movement along the other one as well. So I kind of if I measure a distance with a coordinate or and another collinear coordinate, I kind of get twice the distance for that one, whereas maybe it only is varying one aspect of the data sets. So it's kind of giving equal weight to all coordinates, even if they mean the same thing. So it's not adjusting for if coordinates are repetitive with respect to each other. Okay, so these are reasons why they're kind of, again, blindly doing this without using any supervision of the data. Whereas if you have something where you know things should be the same cluster or the closer far pairs, then these other methods are available, and they're kind of more appropriate. They might be much more appropriate than these two approaches. Okay, on the other side, so this linear DML, it works kind of better if you first normalize. Okay, so if you first normalize the data, it turns out these methods work better. Okay, and the reasons for that are a combination of two things. One, it's a bit technical in some of the arguments, but also it makes it numerically more stable. You don't have to change as far, So it's kind of easier to learn what the right answer is. So you're often better pre-processing with these things and then running these algorithms. And in principle, if you have enough data, it shouldn't make a difference, but you can do better with less data if it starts out pre-normalized. And these are the pros. And so it's generally better than nothing. So if you just have data and you want to use Euclidean distance between it and you haven't done any pre-processing, you're better off normalizing than just computing the Euclidean distance. And they're pretty simple to do. Okay, so it's not a bad idea to do these things. I'm not like, I won't fault you if I see you do it. And it's almost always works better than not doing anything if you're measuring Euclidean distance. And it doesn't really matter which one you use, either the standardization or the 0-1 normalization, whatever you want to do. But if you have differences in the values of things and they have some units to them, this is generally better than not doing anything. Okay, but if you do have a little bit of labels, then you should use one of the LDAs or the linear distance metric learning. Okay, great. So we'll stop there. And we'll start talking about noise and privacy and some other stuff next week.